What if almost all the weight in your body comes from something that has no mass at all? Inside every proton, massless gluons are the secret. In this video, you'll see how gluons, the particles most people never think about, do far more than hold quarks together. They shape the proton and trap energy inside matter. Gluons create nearly all the visible mass in the universe. They aren't just glue, they are excitations of the strong force field. A gluon is a localized ripple in a field. When a quark changes its motion, that change is carried through the field by the gluon. That is how the force moves. Unlike photons, gluons carry the very charge they transmit, color charge. This means gluons can interact with each other, reshaping the field itself. This makes the strong force unique. Instead of weakening with distance like gravity or electricity, the tension between quarks actually grows as you pull them apart. The force does not die away. It responds to separation by building up. Understanding gluons is the key to understanding the very mass of our world. Inside every proton, a restless interaction is happening all the time. Gluons are emitted and absorbed, exchanging color charge between quarks. The mass of the proton is not mostly from the quarks inside it. Most of it comes from the energy of the gluon field and the motion trapped within. That means the weight of ordinary matter is mainly the weight of energy confined inside a self-interacting field. What kind of force becomes stronger when you try to pull it apart? Unlike everyday forces, this interaction pulls inward as distance grows. It forms a tight channel of energy. Because the field remains concentrated, stretching it requires adding even more energy. These aren't just side questions. They go to the very center of what matter is, a system of pure, concentrated activity. This is the first clear picture of what physicists call a flux tube. It's a narrow region of concentrated energy stretching between two quarks. As you pull quarks apart, the tube stretches and the energy builds up. Because energy and mass are interchangeable, something remarkable happens. The field creates a new quark and antiquark pair directly from that stored energy. Instead of isolating one quark, you've created more matter. This is the pair creation barrier. It explains why we never see free quarks. Pulling harder only triggers more creation. This structural feature of the strong force ensures that unbalanced color charge cannot exist freely in our universe. What appears in experiments as a spray of particles is not a failure to isolate quarks. It is the visible signature of a deeper rule. The field tightens, energy accumulates, new matter appears, and balance is restored. That restoration of balance is not a rare event limited to extreme experiments. It is the normal state of matter everywhere. Every proton around you contains quarks that have never existed alone. From the earliest moments after the universe cooled enough for protons to form, quarks have remained confined. They are constantly exchanging gluons, constantly shifting their internal color, but they never separate into free, isolated charges. This is not because the universe lacks the energy to pull them apart. It is because the mechanism itself prevents that separation from ever completing. Whenever a quark is forced away from its partners, the gluon field reorganizes instantly. A flux tube forms. That tube stores energy as it stretches, and if enough energy is supplied, the system responds not by allowing escape, but by creating new quark-antiquark pairs before any single color charge can stand alone. The outcome is always the same. Instead of isolation, you get more color-neutral particles. The process scales with energy, but it does not break. Higher energy does not reveal a free quark. It produces more particles. This consistency across experiments is not a coincidence. It reflects a deeper structure built into the strong force. Electric charge can exist on its own. A single electron can travel through a vacuum, be trapped, measured, and manipulated individually. Color charge cannot do that. The structure of the gluon field forbids it, and this has been true for nearly the entire history of the universe. After the earliest phase of cosmic expansion, when conditions changed, quarks settled into protons and neutrons. Confinement became the stable configuration. Inside stars, inside gas clouds, inside planets, and inside living organisms, the same rule applies. Matter is not made of freely roaming fundamental charges. It is made of quarks permanently bound by a field that does not allow them to separate. So far we have followed what happens when quarks are pulled apart. The field tightens, energy accumulates, and confinement strengthens. But to understand the full behavior of the strong force, we also need to look at the opposite situation. What happens when quarks are pushed closer together? At first, you might expect the force to simply grow stronger as the distance decreases. If that were true, the interior of a proton would be rigid, with quarks locked tightly in place. But experiments show something very different. When physicists probe protons at extremely high energies, they are effectively examining them at extremely short distances. And what they observe is unexpected. At very short distances, the interaction between quarks becomes weaker. Instead of being tightly clamped together, quarks begin to behave almost as if they are free. They still carry color charge. They still exchange gluons. But the strength of the interaction decreases at those small scales. This behavior has been measured in detail using deep inelastic scattering experiments, where high-energy electrons are fired into protons. The electrons bounce off individual quarks in a way that suggests the quarks are not strongly bound at that instant of interaction. This does not contradict confinement, it complements it. The strong force does not have a single fixed strength. It changes depending on the scale being examined. At very small distances, the interaction becomes weak. At larger distances, it becomes strong. The same force produces both behaviors. This property is known as asymptotic freedom. The name describes what happens as the distance between quarks approaches zero. As they come extremely close together, the strength of their interaction decreases. They move more freely, almost like independent particles. But as soon as they attempt to separate beyond that short distance regime, the interaction strengthens rapidly and confinement takes over. To understand why this happens, it is necessary to consider the role of the vacuum. In everyday thinking, empty space is simply nothing. But in quantum field theory, the vacuum is not empty. It is filled with fluctuations. Particle-antiparticle pairs appear briefly and disappear again. Fields are always present, even when no real particles are observed. In electromagnetism, these vacuum fluctuations tend to reduce the effective charge of a particle when viewed from a distance. The vacuum partially screens the charge, making the force appear weaker at larger scales. But the strong force behaves differently because gluons carry color charge themselves. Their fluctuations do not simply screen the charge, they reinforce it. At very short distances, the interaction is reduced, allowing quarks to behave freely. But as the distance increases, the self-interacting gluon field becomes dominant. The vacuum begins to amplify the interaction instead of weakening it. This is called anti-screening, and it is the reason the strong force grows stronger at larger distances. So the behavior of the strong force depends on scale. These two limits, asymptotic freedom and confinement, are two aspects of the same underlying structure. Inside a proton, both of these behaviors exist at once. When quarks move close, they experience weak forces, but when they drift apart, the increasing strength of the gluon field pulls them back. This balance between freedom and confinement is what gives the proton its stability. It is not a rigid object. It is a dynamic system where quarks are constantly moving and interacting. And from that motion, something even more surprising begins to emerge: mass itself. The three quarks inside a proton are surprisingly light. If you add up their intrinsic masses, the total is only a small fraction of the proton's actual mass. The difference does not come from hidden heavy particles, it comes from energy. Inside the proton, quarks are confined to an extremely small region. Because of this, they cannot remain still. Quantum mechanics requires high momentum. The quarks are constantly moving, and that motion contributes kinetic energy. But that is only part of the story. The gluon field surrounding the quarks is not passive. It stores energy as well. Every time quarks exchange gluons, energy is redistributed. The self-interaction of gluons adds even more complexity. The field is constantly fluctuating, reinforcing itself, and carrying energy in its structure. That energy is not separate from the proton. It is part of what the proton is. When you combine the kinetic energy of the quarks with the energy stored in the gluon field, you get the total energy of the proton. And according to the relation between energy and mass, that energy appears as mass. So when you measure the mass of a proton, you are not primarily measuring its quarks, but the energy of a dynamic system. A proton is a balance between motion and field energy, existing at the point where these effects stabilize. The interior is a fluctuating population of gluons and short-lived quark pairs that contribute to the overall energy. Experiments reveal a complex distribution of energy shared among quarks and gluons. Almost all the mass of ordinary matter comes from this confined energy within protons and neutrons. Mass is simply a measure of energy locked into stable configurations. Under certain conditions, quarks are not permanently bound, forming structures quite different from the stable protons we know. Without the strong force field's energy, the mass of matter would collapse toward the tiny intrinsic masses of the quarks themselves. Gluons carry color charge, leading to self-interaction and anti-screening, which eventually results in confinement. This confinement stores energy, and it is this stored energy that we perceive as the mass of ordinary matter. In the extreme heat of the Big Bang, quarks move freely in a state called Quark-Gluon plasma. As the universe cooled, the strong force intensified, pulling quarks into the bound particles that form our world. Confinement isn't just a subatomic detail. It's a phase the entire universe settled into as it expanded. Today, scientists recreate this primordial state by colliding nuclei at energies high enough to melt protons back into a plasma. It reminds us that mass is not just about what matter is made of, but how its fundamental fields interact. In that moment, quarks and gluons are no longer restricted to single protons or neutrons. They move within a small droplet of quark-gluon plasma, interacting across the entire region. The system behaves almost like a fluid, with particles flowing and exchanging energy in a way that reflects the underlying field dynamics. But this state does not last. The system expands and cools rapidly. As it cools, the same scale-dependent behavior takes over again. The strong coupling increases at the relevant distances. Confinement returns. Quarks reorganize into protons, neutrons, and other particles. The plasma condenses back into familiar matter. What is important here is not just that this transition happens, but that it happens in a consistent way. In both the early universe and in laboratory experiments, the same pattern appears. At extremely high energies and short distances, quarks behave with relative freedom. At lower energies and larger distances, confinement dominates. These are not separate regimes created by different forces. They are two limits of the same interaction. Inside a proton, both of these behaviors are present at once. At very short distances, quarks move with relative ease because the interaction is weak at that scale. But as they attempt to separate even slightly, the increasing strength of the gluon field stores energy and prevents them from escaping. The proton exists because of this balance. Its size, its stability, and its mass all emerge from the interplay between motion and confinement. This means that the strong force is not simply a force that binds particles together. It is a system that defines how energy is distributed and stored across different scales. The fact that gluons carry color charge leads to their self-interaction. That self-interaction leads to a vacuum that behaves differently from empty space in electromagnetism. Instead of weakening the force, the vacuum strengthens it at larger distances. That strengthening leads to confinement, and confinement leads to the storage of energy that appears as mass. At this point, the chain of reasoning becomes clear. A single structural feature, the fact that the carrier of the force carries its own charge, leads step by step to the properties of matter we observe. The behavior of the strong force is not an added detail. It is the foundation of how matter acquires weight. And this brings us back to a more direct question. If gluons play such a central role, if they shape the field, store energy, and generate mass, then what exactly are they? Are they built from something smaller, the way protons are built from quarks, or do they represent a different kind of fundamental entity? To answer that, we need to step away from the idea that every particle must be made of smaller pieces and look instead at how modern physics defines what a particle actually is. To answer that, we need to change the way we think about particles themselves. In everyday language, a particle sounds like a tiny object, something with a definite size, a small piece of matter that could, in principle, be broken into smaller pieces. But in modern physics, that picture no longer holds at the most fundamental level. Instead, particles are understood as excitations of underlying fields. The field is primary. The particle is a localized disturbance within that field. The electromagnetic field gives rise to photons. The strong interaction field gives rise to gluons. In that sense, a gluon is not made of smaller components in the way a proton is made of quarks. It is a ripple in the strong force field itself. Asking what it is made of is similar to asking what a wave on the surface of water is made of. The wave is not built from smaller waves. It is a pattern that exists within the medium. What makes the gluon unusual is not hidden structure inside it, but the properties it carries. A gluon carries color charge, and because of that, it participates in the very interaction it mediates. This is what gives rise to all the behavior we have traced. The self-interaction of gluons reshapes the vacuum. It causes the strength of the force to depend on scale, leading to confinement at large distances, and allows quarks to move more freely at very short distances. None of this requires smaller building blocks. It emerges from the structure of the field and the symmetry that governs it. That symmetry is described by a mathematical framework known as SU3, Sansenpoi at Senpei. It defines how color charge behaves and how it can change. A quark can change from one color to another by emitting or absorbing a gluon. Each possible change corresponds to a specific type of gluon. When all the allowed transformations are accounted for, there are 8 independent gluon states. This number is not arbitrary. It follows directly from the internal structure of the symmetry. If you try to count all possible combinations of color and anticolor, you might initially expect 9. But one combination does not lead to an independent interaction. It represents a perfectly balanced state. When that redundant possibility is removed, 8 distinct gluons remain. Each one plays a role in color exchange. Because gluons themselves carry color, they can interact with other gluons. This creates a rich and complex network. But that complexity does not come from smaller parts hidden inside the gluon. It comes from the rules governing how color charge can change and combine. Experiments support this picture. When physicists probe interactions at high energies, they are looking for substructure. But what we observe is consistent with gluons behaving as elementary particles. Their structure is not composite. This leads to an important conclusion. The richness of the strong force does not come from layers of smaller objects. It comes from the way the field behaves. The gluon is not a tiny piece of matter. It is a self-interacting ripple in a field that determines how mass emerges. So the answer is not another particle. It is the field itself, not ingredients, but a pattern. And that pattern gives structure to matter. The strong force is the mechanism that locks energy into stable forms. From that locked energy comes mass. From mass comes the structure of atoms, planets, and everything we can touch. All of it traces back to the carrier of the force. That single feature builds the weight of the visible universe from energy that refuses to disperse.